Welcome back, welcome back. Let's remove an unrealistic assumption. I've been assuming that we know sigma, the population standard deviation of 20 up here. And in the dance of the means, every confidence interval is of the same length because MOE I'm using here, 8.765, is calculated as sigma 20 divided by square root of 20, and that's this MOE here. And if I take some further samples, each one has the same MOE, 8.7 here, and they're all the same length. Now, let's assume we don't know the population. I simply have to click down here, assume sigma is, read the pop out if you like, assume sigma is unknown. Some of these intervals get longer, some get shorter. Let's do that again. Known, they're all the same length. Unknown, some get longer, some get shorter. If sigma is unknown, then for each sample, and remember we only ever have one sample at a time, each sample we use the S, the sample standard deviation, as our estimate of sigma. And so MOE will change from sample to sample. So keep an eye here as we go through, take sample, and this happens to have a slightly shorter standard deviation, so MOE is a little shorter. They're bouncing around near 20. Here's a slightly longer one, 23, and MOE is about 11, and we have the latest confidence interval here. It's a little bit longer than some of the previous ones. So the dance of the confidence intervals with varying length intervals, because we don't know sigma, and for each sample we use S, the sample standard deviation, to calculate the interval. Oh, here's one that must have had a very short S, very short sample standard deviation, so we happen to get a short confidence interval. If we show capture, then because they're 95% intervals, in the long run we will get very close to 95.0, even though they vary in length. The statistical theory is worked out, and we use the T distribution as well as S to calculate the confidence interval in each case, and once again we have 95% intervals. Now let's suppose we took much smaller samples, let's say 6. Of course we'd have a wider dance of the means and on average longer confidence intervals, but look at the extent to which they vary in length. Here's a short one, and here's one that's roughly twice as long. Another very long one, another quite short one. And we shouldn't be surprised about that, because the standard deviation S of small samples is not nearly as good an estimate of sigma, the population standard deviation, as it would be for large samples. And so we'd expect the lengths of confidence intervals to bounce around very much more for very small samples. If we go down to an extremely small sample, say n equals 3, then we get very long confidence intervals on average, but even more extreme variation in confidence interval length. We'll still get 95% capturing, but with very great fluctuations in length. And in fact, for n this small, the confidence interval length of a single confidence interval is really not much use, because if we repeated the experiment, we might get an interval 3 times as long, or only 1/3 as long. And so for very, very small samples, confidence intervals are not much use for indicating precision, the extent of uncertainty in our estimate. A bit more about the T distribution. I'm on the normal and T page of ESCI, and this blue curve is a normal distribution. I can show instead the T distribution, this red curve, and I can compare the two. And this is for degrees of freedom for the T of 10. If I go down to smaller degrees of freedom, the two curves get more and more different, down to the ridiculously small 1 degree of freedom corresponding to a sample of n equals 2, and they're very different indeed. As I go up to higher number of degrees of freedom, 30 and beyond, 40 and 50, the two curves become almost indistinguishable. Let's go back to sample of size 20, so 19 degrees of freedom, and just look at t. And let's use this page to find the critical value of t that I need to calculate a 95% confidence interval without assuming that sigma is known. So what I want is two tails and areas labelled, and I want to move the cursors so that I get an area of 0.95 there. So I'm going to move them out. Fair way. There we go. Getting close to 0.95. Oh, I've overshot. Right, here we go. So for t of 2.09, that's the critical value of t for 19 degrees of freedom, and that's what I'd use to calculate the 95% confidence interval when we have a sample of size n equals 20 and we don't know sigma, as is usually the case.